So I shall begin by recalling the definition of a characteristic function of a random variable x. So let x be a random variable defined characteristic function px of t as px of t is equal to expectation of e power I t x. Okay, and so if x is continuous, with density function fx of x, then px of t is equal to so integral minus infinity to infinity e power I t x fx of x dx. Okay, if x takes discrete values, x is discrete. Then so this time it will be summation so you again write e power I t, let us write xn, doesn't matter, xn probability of x equals xn, or just write f of xn just to keep the form the same, where x takes values, so summation is over and x values x1 blah 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 and fxx is the density, is the mass function of x. Okay, I started with listed some properties. Let me list that once again, and then we will do examples. So let me just quickly deal with at least some basic properties. So properties of characteristic functions. So sometimes we just simply write phi instead of phi x, but so phi is equal to phi x of t be characteristic function of a random variable x. So then number one, phi of 0 equals 1 and mod phi x of t is less than or equal to 1 for all t real numbers. Okay, so is this obvious? Okay, you just have to put t equals 0. Let's only be concerned about this continuous or the discrete case. When you put t equals 0, or you can just directly apply the definition also. In the definition, you put here t equal phi x of 0 is expectation of e power 0, or that is just e of 1. So that's equal to 1. So 1 is a constant function 1, or you can think of it as a random variable, which is the indicator function of the whole space omega. Either way, it's the same thing. So that's equal to 1. And what about this one? Okay, so uh, yeah, you can, you see, basically because x takes only real values, so you put here absolute value of this is equal to absolute value of the expectation, which is less than or equal to absolute value, less than or equal to expectation of the absolute value. But e power itx, x takes only real values, so its absolute value is 1. So e of 1 again, so which is equal to 1. So I told you the proof orally. Yeah, this is not at all difficult. Phi is uniformly continuous. Uh, 3. Phi is non-negative, non-negative, definite. Definite. So what does this mean? Okay. So yeah, what this means is that if T1, T1, T2, Tn are any real numbers, and Z1, Z2, Zn are complex numbers, then just look at this summation. Yeah, so phi of Tj minus Tk, Zj, Z, Zj, Zk bar, Zj, Zk bar. Okay, so this is always greater than or equal to 0. Anand. Okay, this summation is over J and K. Summation is over J and K. Do I want to prove this? Maybe. So let me just say this. Yeah, you can think of it this way. So suppose I make a matrix out of this. Okay. So I have fixed my T1, T2, Tn, and then I get n square possibilities, Tj minus Tk. All right, so j can equal k also, doesn't matter. I get a, therefore, n square elements, which I can write in the form of a matrix. So the matrix is just P, the ijth entry is Tj minus Tk. All right. So think of it as a matrix, n cross n matrix. And then here you write the matrix, maybe Z1 bar. Okay. So I just write Z for the column vector, and then write here Z, and then write Z bar transpose. Okay, so here I should write Z bar, and doesn't matter which side, but I should write here Z transpose. I always write Z as a column vector, Z1 blah 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 Z. And now, so what this means is that this matrix is non-negative definite. You might have studied in linear algebra notion of positive definite matrices or non-negative definite matrices. So what this, when you compute this, this is now a row vector. So 1 cross n, n by n, and n by 1. So in effect, then it's just a number, and it makes sense to say this is bigger than or equal to 0, and that's exactly what is asserted. Okay, so let me. Uh, I would like to give some proof of this, but the problem is not much time. So I'll be very brief and write this. Okay, I don't want to discuss two. Probably you people have studied uniform continuity. I'm not sure. I don't know if you have studied it. Let me not talk about that. Not that it's difficult, but I want to skip a few proofs because there will be no time to discuss everything. So what? So let's just look at this quantity in here. Summation phi of tj minus tk zj zk bar, and here summation is over j comma k. I just write it uh, by expanding the definition, unpacking the definition of this, then I get integral. So phi of tj minus tk, that will be e power I times tj minus tk x, so zj zk bar, and then sorry, no, not phi, f, the density function fx dx, and here it is minus infinity to infinity j comma k. So I can take this inside. Okay, so integral minus infinity infinity. So this is I, okay. So I rewrite it in this fashion: zj e power I times t t whatever tj x times zk bar uh, e power I minus I tk x fx dx. There is a summation here outside. So, okay, so uh, so summation is over j and k. You can rewrite it in this particular fashion: minus infinity infinity. This is a crucial point. So you write here z1 e power it1 x plus blah 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 zn e power itn x, and then you write the bar of this. Okay, so when I do that and expand it, I get exactly this: t1 z1 bar t power e power minus itx, and then plus blah 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 plus zn bar e power minus itn x. X always is real, by the way, so times fx dx. And now does that look? Okay, this is equal to integral minus infinity infinity observed. So this is some complex vector and its conjugate. So this is z1 e power itx plus zn e power itx. Okay, t1 and then tn whole square, norm square fx dx. Now fx, of course, is density, so non-negative, and this is anyways uh, non-negative, so the function is therefore evaluated integral is therefore greater than or equal to 0. That's it. So that completes the proof. Now, one important result that we will require later. For that purpose, I state this. There will be several results which will be needed later on. So I just state the theorem. So suppose that uh, phi. So this means kth derivative. Suppose this exists and is finite. So that's what it means to say it exists. Then, so yeah, okay, I probably will require the converse of this nevertheless. Then expectation of this exists and is finite if k is even. K is even, and expectation of absolute value of k minus 1 is finite if k is odd. Okay, so we will do examples shortly, but let me just state the other part also. Suppose that is a kind of a converse expectation of absolute value of x power k is finite. Okay, then you have a Taylor series expansion with the remainder phi x of t. So some of these results require complex analysis to give a proof, but we just skip it. Okay, e of x power j by j factorial. I mean, it should not be surprising that such a thing should be valid in some, yeah. J equals 0 to k. Here, it power k plus small o of t power k. And this notation means that it goes to 0 as, I mean, so this divided by t power k goes to 0 as uh, t goes to infinity. That's the meaning of this. So, so this is what is called small o notation. Okay. So roughly it means higher order terms, but the higher order simply means that something strictly bigger than k, but need not be k plus 1 or k plus 2, but never mind. Okay, so just this term, what this means is that it goes to 0. So when divided by, so you, this is some function which when divided by t power k goes to 0 as t goes to infinity. That's the meaning of this. So small o notation. Let me not expand on that. I just told you what it means. So okay. Um, yeah. So here is another property. So which we'll state as a theorem. If x and y are independent random variables, then phi of x plus y evaluated at t is just phi xt times phi yt. Okay, and we can give a proof of this. It's not at all difficult. One small subtle point, but let me write it formally. So phi of x plus y of t is expectation of e power I times t x plus y. So I write it like this. Okay, x plus y, first step. Let's write the definition. So this is, of course, so I just scroll down. So this is equal to just property of the exponential e power itx times e power ity. Now, so if x and y are independent, then e power itx and e power ity are also independent, and therefore I have expectation of product of two independent random variables, which is therefore product of the expectations. But one word of caution, you have this I here. So this is complex. So one is not allowed to use such heuristics. We have to make things slightly more rigorous. So the best way to do that is just expand it. E of, in fact, what is the meaning of e power itx? Okay, by definition, it's just cos of tx plus I times sine of tx. Okay, and now, so this is cos of ty. So even I just, nobody ever asked me why, how to make sense of this, but you, if you want to just everything dual, I mean in the realm of real numbers, you have to separate the real and imaginary part and then write the integration. Anyway, so this is just, you write it like this: cos of ty plus I times sine of ty, and now you just write it, write it out as a product, and then separate the real and imaginary part, and then use the fact that if x and y are independent, so are cos t x, cos t y, and sin t x, sin t y, all possible combinations. And then, so you write it here. I'm not going to write it completely. Okay. Yeah, well, and yeah, separate it out. Something, and this becomes, okay, a of x comma y. We can compute it just by direct multiplication plus I times expectation of b of x comma y, just by repeatedly using that thing. And now, so from the very form of this, you would know that this is, yeah, you expand this, okay? It's not a very complicated thing. It's a very simple exercise. So this becomes expectation of, yeah, you expand it out and then regroup it and so on. So this becomes ITX. So all I want to say is some caution is required before you can write like this. So long as you exercise that caution, everything is completely justified. Mind you, when we talk about real, I mean, random variables, they were always real valued. However, we introduce this complex number I. So just you are not allowed to simply manipulate this thing as if you are working only with real numbers. That is why a bit of caution is required. Okay. So after this, then this is fx, py of t. That's it. Okay. So now we will do examples. So the simplest random variable x is the Bernoulli random variable with parameter p. So probability, so it takes only two values, 0 and 1, and probability x equals 0 is q, probability x equals 1 is p. So just apply the definition. So always write the first step of thing, your proof, whatever, or computation must be the definition, e power itx. And since x takes only two values, you can just explicitly write it. This is e power it 0 times probability x equals 0 plus e power it times it 1 times probability x equals 1. So this is of course 1. So q plus e power it uh, p times e power it. Yeah. Next example is of course binomial random variable. So sorry, binomial with parameter n comma p. So this is your x now. And then what is phi x? Phi x of t. Well, you can use the theorem that we just now proved. So x is equal to x1 plus blah 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 plus x, and they are all independent, and each xi is Bernoulli with the parameter p, and so xi are independent. Say independent. Okay, so this means that this is phi of x1t dot 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 phi of xnt. They are all identically distributed, so this is just phi x1 power n, and you know you have already computed that q plus p power it whole power n. And you may try some discrete random variable. For example, this is exercise. I don't want to discuss this for Poisson with parameter lambda. Compute phi of x. Okay. Now I'll discuss some continuous random variables. So exponential. So you see, you are going to have to integrate things which involve complex numbers. So the meaning of the operation should be clearly understood, and one should not just blindly treat that as a real number and manipulate them. Sometimes you get correct answer, but there are a lot of subtleties, and you will study contour integration, and at that time you can give a very rigorous proof for treating complex parameter. And there's a theory, so one just cannot bypass that theory. But sometimes you use some trick to reduce it to the real variable case. Okay, so now let us do this. What is the thing? So exponential with parameter lambda. So the distribution, the density, so fx, so x is equal to x exponential. So fx of x is equal to lambda e power minus lambda x, and of course x is bigger than or equal to 0. So what is this phi x of t? This is equal to integral minus infinity infinity, but then the density function is concentrated only on the part 0 to plus infinity. So you get 0 to infinity e power itx, and then lambda, that's a constant, I can pull it out, and then I have e power minus lambda x dt. Okay, now you can rewrite this e power itx as lambda integral 0 to infinity. So itx is cos tx plus I sin tx. So I times. So that this is the meaning of this integral anyway. E power, yeah, sin tx e power I. Sorry, here there's an x. I'm sorry, I just messed it up a bit, confused the thing. T is of course a variable here, but so far as this integration is concerned, the integration is with respect to x. So here I left out the parameter, multiple typographical errors. One has to be careful. So e power minus lambda x dx. And you people have studied in 12th standard how to integrate these type of things. Mind you, lambda is positive, so this whatever you do, finally it will turn out to be something finite quantity. And so that's a okay. I should close this parenthesis because this lambda is outside. But when you do that, and finally it turns out that this is lambda by something. Yeah, lambda minus it. Okay, is what you get. So that you may sort of heuristically guess by looking at this. This is e power minus lambda minus it x dx. So if you treat it as if this was a real variable, this whole integral would have become 1 by lambda minus it, and that is why you get this. But that's not the right way to do it. This is the way to do it, unless you perform what is called contour integration of complex valued functions. Anyway, I'm not going to even talk about that. No time. Anyway. You will learn that. You will learn those techniques when you take the course on one complex variable, complex analysis. Okay, so the next one we want to compute is this. So I'm just continuing with examples. Okay, so I don't know if I got the number, maybe 4 or 5. Example 5. So this is a normal variate. X is equal to n01. Okay. We will do the more general one. X is equal to normal variate with mean mu and variance sigma square. We will do in a minute, but first let us do this. Okay. So phi of x of t is integral minus infinity to infinity. Okay, I wrote 1 by root 2 pi first, it doesn't matter. E power itx, and then e power, what is it, minus x square by 2 dx. Okay, now instead of doing this, it is better to work with the moment generating function, because precisely because there is a complex number involved in here. Okay, so better to work with the mx of t. I suppose you could use this, split it into cos and sine. Then you will realize that it is not so easy to integrate as in the case of exponential. Okay, the exponential function, for the exponential distribution, it didn't involve square here. Now there's a square involved. So that UV formula is not easy to apply. So better to do this. This is a moment generating function, and that is minus infinity e power tx. Okay, e power minus x square by 2 dx. There's a 1 by root 2 pi. I should not forget this. This is equal to 1 by root 2 pi integral minus infinity e power minus of. So only when you have perfect square, you can integrate this basically. So complete the square. So I have x square. So this divided by 2 will be written here. Minus 2tx you may add and subtract t square. Okay, so e power minus t square by 2 dt dx. Integration is with respect to x. Therefore, I may just simply pull out the e power minus t square by 2. Is it minus t square by 2 or plus t square? It should be plus, because you see there's a minus t square, so I must compensate it by adding plus, adding t square by 2. So this is e power t square by 2, 1 by root 2 pi, and integral minus infinity, infinity e power minus of x minus t whole square divided by 2 d dx. But this is just the density function of the random variate with mean equal to mu t. Okay, so this whole stuff becomes 1, leaving me with e power t square by 2. And now you see I have a function. This is my function mt, mx of t. And you see this is of course t is real numbers. But now I can extend it, and it makes perfect sense to think of t as a complex variable, and I get e power t square by 2. That's a very perfectly valid, complex valued function of a complex variable. So think of it as a complex, think of t as a complex variable. Think of t as a complex parameter. Then you can compute phi t of x. Phi x of t is equal to mx of it, which is equal to e power minus t square by 2. And this is an extremely important result. Okay, so later on when you study Fourier transform, we will see that, yeah, the Fourier transform of this. Anyway, so this will make more meaning at that time. Okay. Yeah, so one can go on calculating like this. I will do just one more. This okay. I told you I want to also do. So example, when x is normal with mean mu and variance sigma square, then okay, you write y is equal to x minus mu by sigma, I suppose, sigma square. Variance of y will have to pull out sigma square. Okay, fine. So it is sigma is n01. Okay. So you know already. We know we know phi y of t. Okay, and we want phi x of t. So you make use of the following simple observation, and I will state it as a sort of a lemma or something. Very simple. Suppose that x is equal to ay plus b. Okay, then phi x of t is equal to, how is it related to phi y of t? This is the thing. Okay, so expectation of e power itx, e power it, in the place of x you write ay plus b. Okay, now this can be split. So this is e power, yeah, e power it ay times e power it b, but that's just a constant factor. So e power it b times e of e power it ay. But that's just, this is simply e power itb times phi y of at. So now you know it for this. So now substitute for yeah. So I have to write. I have. So this. So we know this, and now write x is equal to a mu sigma y plus mu. So you know your a and b, and from there you can write it. I'm not going to complete it. Okay. Yeah, gamma distribution. Hmm. Maybe I. Hmm. This is important, so I just state it, but not discuss it in detail. In fact, I don't think we'll be able to do it. So next example, gamma distribution. So mind you, gamma distribution has two parameters. One is lambda, the other is S, and with density. Uh, so what is it? Yeah, there'll be 1 by gamma S, lambda power S, and x power S minus 1, and e power minus lambda x. Okay, so this is a thing. And we want to compute, so phi x of t, this is equal to, so here x is bigger than or equal to 0. So integral minus, yeah, 0 to infinity. So gamma, this lambda power s is a constant, so I can write lambda power s by gamma s here outside. And now I write x power s minus 1, e power minus lambda x, and then e power itx dx. Okay, so this is equal to, so some grouping is required. I've already done part of it here. 0 to infinity x power s minus 1, e power minus lambda. Okay, now I think minus lambda, I write minus it here, so that this minus lambda, and then times x here. Okay, and dx. So this is lambda power s, not lambda square. Lambda power s. Okay. Now, yeah, if only this were a real number, then we know how to compute this. Yeah, and that value, whatever it is, after you reparameterize it by putting lambda minus itx is equal to some y, you can rewrite it. But the problem is, this is not a real number, and that type of substitution is not quite legal. Nevertheless, after giving some justification, you can see that, okay, this is going to be lambda power s, gamma s, and this integral is just gamma s by lambda minus it whole power s. So this gamma s and this cancels, I get lambda minus it, lambda divided by lambda minus it whole power s. Okay. We will nevertheless use this formula. Yeah, if one learns complex analysis, first of all, the gamma function has to be thought of as a meromorphic function defined on the whole complex plane, and lot of some justification. Yeah, I mean, sorry, I cannot give the justification involved in making this rigorous. That's not part of this course anyway. So you will learn that justification in your complex analysis course. Okay. So yeah. Okay. So uh, some special cases are interesting, but let me not go into that. I think I should now talk about some additional properties, etc. So, okay, I think, okay, let us do one example maybe. Example. So, if you recall, we had this chi-square distribution. This arose in two different ways. Okay, one is uh, so z, writing z equal to x square, where x is equal to n01, and the other one is other justification is uh, this chi-square distribution. Okay, I have already used a symbol z. Z is equal to gamma, lambda is half, and s is also half. So if you use this, what is a characteristic function? Phi z of t, you just put lambda equals half, and this is equal to half. So what you get is so 1 by 2 power 1 by 2, so 1 by root 2. Okay, let me write that. Or let us just write everything together and then. So lambda is 1 by 2, that means denominator is multiplied by 2. And so when I 2 times lambda, that will become 1 minus 2 times it. Okay, and that is under square root. S is equal to half. See, so power half. Okay, and just stop with that. Uh, yeah, there is another distribution which is also equally important. While studying characteristic chi-square distribution, this is what they say: chi-square distribution of degree 1. Chi-square distribution, chi-square distribution of degree d. Degree d is equal to z x1 square plus blah 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 plus x d square. Sorry, x d square. So what is x? X is always this n01. Each xj and x1, x2, blah blah blah, xd are independent random variables. And in this case, what is phi of z of t? So because it's this one, these are all independent. So x1 square, blah blah blah, xd square, they are also independent. So I get here x1 square, and they are all identically distributed also. X1 square t, if you like, I can write here phi of xn square, xd square, xd square, so not x of d square. Okay, t, and of course each one of them is 1 by square root of whatever, 1 by uh, lambda minus it power half, and that raised to d by 2. Okay, and yeah, so this also has the property. So z is also, note, z is also equal to gamma half, sorry, there is no lambda here, lambda equal 2 lambda, it has become 2 lambda, so it is just 1. Okay. I was thinking of something and then wrote something else. 2it, yeah. So gamma is half and then S value is D. Now use the same thing. In the place of S, you put D, okay. And in the place of lambda, you put half and you get exactly, uh, so in the place of S, what did I do? Is there some, yeah, S also, S is D by 2, okay. S is equal to D by 2. So I wrote maybe D, that's wrong. Because degree 1 corresponds to half. Okay. And now you can check that this also correspond. I mean, the characteristic functions computed either way gives you the same answer. Okay. Now what? Okay. Now I have not much time. Uh, yeah. So this I want to talk about inversion and continuity. This is the next section. Okay. So the main thing is, if you know, so this is the main thing. If so, phi determines phi x of t determines f of x, fx. You see, when you have the distribution function, that determines your yeah, phi x of t. Okay, but you can also invert the process. This is the main thing. Uh, so some special cases you can write actually, suppose for example x is continuous, you can write a formula for the density which is valid at each point where f is differentiable. Okay, so or capital little f density function is differentiable. So so this is the main inversion. This is what we mean by inversion formula. Okay. So I want to expand this a little. So this doesn't say how to express this, yeah, fx of x in terms of phi x of t. So let us do it step by step in special cases. Okay, suppose that, so this is a theorem. Suppose that x is a continuous random variable with density f, and characteristic function. So characteristic function phi. Okay, then so you can write the value of f of x is equal to, there's a 1 by 2 pi factor integral minus infinity to infinity e power minus itx x phi of t dt. Mind you, this time, see, the variable is t here. The integration is with respect to t. X is a constant, so rather x is fixed. X varies in real number. But thing is, you need to put some hypothesis on f. So provided f x is differentiable at x. Yeah. So what? So in particular, if fx is differentiable, if you know the density is differentiable, and if you have a characteristic function, so this is what is called inversion formula, or this is part of what is called the Fourier inversion theorem, so on. I mean, when you study, yeah, in this course, towards the end, some fair bit of analysis is assumed, um, but we, in the cases that we will actually have to use these, um, you will work with very specific functions. So anyway, so specific calculations. Yeah, even so, you can illustrate, you can check these things. Yeah. Uh, this is typically the case with um, probability theory. It will borrow results from various sources in mathematics, um, which are at a rather deep level. That's because the, on the one hand, it's nature of the subject, and also on the other hand, things, you cannot dwell at elementary level for too long. You have to proceed further and learn. If you have to learn some non-trivial result in any subject, you will see that you have to borrow results from various other branches of mathematics. At least to illustrate it, we do these things. Okay. I have taken the route as in this particular book, but perhaps there are other ways. I know that there are other ways of doing central limit theorem. Okay, so our aim is to understand central limit theorem and give an indication of proof, and the proof will involve this type of considerations. You will see. Okay, so yeah, so let me make this statement. Two random variables. Random variables x and y have the same characteristic function, if and only if they have the same, so same distribution function. This is what we mean by saying that the characteristic function determines the distribution function. There is some amount of discussion in this, but I won't do this. Rather, what I will do is talk about the notion of limit of the distribution sense. So, yeah, suppose that f1, f2, fn, blah blah blah, are distributions of some sequence of random variable x1, x2, xn, dot dot dot. Okay. Yeah. Let f be a distribution. F be the distribution function for random variable x. We say that fn of x, yeah, fn of x, sorry, fn of little x, if limit n going to infinity, fn of x is equal to f of x at all points at which f is continuous. F is continuous. And mind you, f being a monotone function, it will only have countably many discontinuities. So at almost all points, it must have the same thing. Yeah, without this requirement, you can have some very strange things happening, and I don't have the time to discuss that. So this is the thing, and now the thing is, yeah, this is the important theorem. Suppose that phi of t is equal to limit n going to infinity of phi n of t exists and is continuous, at 0. Continuous at 0. Okay. I need more space. Okay. Then, yeah, where phi n of t are characteristic functions. Okay. Then phi is the uh, characteristic function of a distribution of a random variable, I can say, of a random variable x with the distribution function distribution f, where and you can even say what f is, how f is related to this fn. Okay, so this, let me write it as phi of xn of t. So where limit n going to infinity fn is equal to f. So in the previous sense, okay. So this is the main thing. In other words, let me tell you what is happening here. So suppose you have a sequence of random variables. You can compute their characteristic functions, and if it so turns out that they have limit, pointwise limit, it exists, and the limit function is continuous. Okay, so I'm calling that function phi of t. Then phi of t actually is a characteristic function of a random variable, and that random variable has distribution function f, where f is given by limit n going to infinity of fn. So this is the main theorem, and this will be extremely useful. See, you want to say, okay, I have a sequence of random variables. I want to say this sequence of random variables converges to a random variable x. Okay, what does it mean to say? Yeah, let us say a sequence of random variable converges uh, in distribution. Okay, what does that mean? It means that the corresponding distribution functions fn of x goes to f. Okay, so you want to say a sequence of random variables converges to a random variable. The simplest way to do that is find the limit of the characteristic functions and check that the limit exists and is continuous. Okay, now you got hold of then that function, limit function, is indeed characteristic function of a random variable. Okay, and then what is its distribution function? You just compute this limit n going to infinity of fn of x. We can compute it. I mean, I can put x here and write equal, but then the equality is only whenever this, I mean, so anyway, this is just as a limit in the sense of distribution functions. So this has to be understood in a proper way. Okay. So yeah. So these type of results sort of tell you that characteristic functions are very useful when you want to study. Now, see, instead of studying the distribution is already captured by random the characteristic function. Um, you might want to say that, well, I mean, uh, I mean, if the moments existed, then what you can say and so on. The thing is, moments may not exist quite often, but characteristic functions always make sense for a given distribution, okay, or a given random variable. Now, if I have a sequence of random variables, then there is a notion of sequence. There are several notions of random variable, limit of a sequence of random variables to be another random variable. There are several notions of limits. One such is this distribution. So you look at the corresponding distribution functions and see if it goes to the distribution function in this sense. Okay. If that happens, then you can say xn goes to x in the distribution sense or in the weak sense. All right. Okay. Yeah. So this, um, in order to compute, so you can think of it as a means for computing limit of random variables in the distribution sense or in the weak sense. Okay, so that is how this theorem will be used. All right, I think maybe I will stop here for today, or I just maybe do one exercise and then stop. So exercise. This is also given in the book. Suppose that phi is the characteristic function of a random variable x, then show that phi bar is also a characteristic function. Similarly, real part of phi bar, real part of phi, and yeah, what is the other one? So yeah, I think mod phi square, so on. Okay, so let us do this phi bar first. What is the meaning of phi bar of t? Of course, this is equal to yeah. So phi of t is what expectation of e power I t x. Okay, sorry. So whole bar, but that same thing as phi of I t x bar. Bar stands for complex conjugation. This is e of e power minus I t x. So this is phi of. Okay, let me write one more step as a matter of abundant caution. Phi of so phi of minus x of t. Okay. So now if you have this phi x, phi and phi bar, then you can make a phi bar square, right? So it will be product of the two. So suppose x1, x2 are independent random variables where x1 has the same distribution. Okay, x1 has the same distribution as x, and x2 has the same distribution as minus x. Then can see this thing what I'm writing. Then phi of x1 plus x2 of t, this is equal to phi x1 t because of independence times phi of x2 of t, and just now we saw that this is same thing as mod phi square. Apparently mod phi of x, mod phi need not be a characteristic function of a distribution. Okay, what is the other one? So real part, I just tell you briefly and you can work it out. So for the real part of phi, consider the random variable uh, z, yeah, which is equal to, well, x with probability half. I'll tell you what that means, and minus x with probability half. Okay, so in other words, this distribution you can think of it as being defined in 0, 1 cross omega. So you toss a coin, or ht I may write, ht, unbiased coin. So if h turns up, then it is a random variable. So if h is a first coordinate, then it is like x. So, and if tail is the first coordinate, then it is the function is actually minus x. So that's a way to think of my z. Okay, to real numbers. Then phi of z, phi z, so phi z of t is, well, it involves both this one. So it is just so it's a sort of combination of both discrete and continuous or whatever. So this will turn out to be equal to 1/2 phi x of t plus 1/2 phi minus x of t. This is equal to, yeah, real part of. I'll stop here. I have 2 more lectures, and next lecture I hope to prove uh, state and prove this central limit theorem. Then we'll work out some examples. This is the plan for the next 2 lectures. Okay. All right. That's all for today.
Sir,
Yes.
so how many classes do we have left?
2 more.
Okay.
I don't know if it is okay for me to lecture on 9th. Last day of the semester is 8th of March, 8th of May. If I can lecture for one more day, I can utilize that time for doing many more problems. I hope to work out a few more examples and upload it by Friday or Saturday. I'm also extremely busy with so many other things. That's why I've not been able to do that systematically. But nevertheless, there are these tutorials. I hope that will help you also. But what I can do, you see, do you have 1 week of gap, right?
Yes, sir.
I can conduct the tutorials during that time. It will not be lecture. I'll just work out some problems uh, through the next week, or at least let me. Can I do that on Monday? See, I just don't want to schedule a class outside of the thing without having the support of those who want to attend. If you don't want to attend, that's fine. I mean, if you don't want to attend my lecture also, that's fine. I will not feel hurt or anything. But it's just that you should not feel compelled to attend. If you have some important thing coming up, I have no idea. I can lecture on 9th of May, and that will be my last lecture. And having said that, I can conduct one tutorial sometime towards the end. But then you will be traveling, I suppose. I don't know. I think many of you people will have to come to the camp. You all have to come to the campus to write the exam anyway. So okay, definitely two more lectures. That is next week. That is well within the timetable. And then I will let you know on Monday whether I'll give a lecture on 9th of May. Okay?
Yes.
All right.
Sir.
Thank you, sir.
You're welcome.